Welcome to Nonlinear Optics, live from Jena. Happy New Year, first of all. I know the situation is not particularly happy so far, but I think there's very good hope that it will improve. Well, you still see my Christmas tree. This is not by accident. This is actually, if you look at the traditions, then Christmas lasts at least 12 days. Well, 12 or 13 days, so from the 25th to the 6th or to the 5th, depending on how 12 is interpreted in Christian counting. So the 6th, this is the day of the three wise men, or some say Little Christmas, or the 12th night. Strictly speaking, Christmas actually goes until the 2nd of February, so this is 40 days after Christmas. 40, this is some kind of a magic number in the Bible. So just a little bit of education. So now if you see the used Christmas trees on the streets already, then you know this is not according to the traditions. And maybe some of my fellow Jena or Thuringian students, maybe they consider that. Yeah, so the Christmas tree should stay at least until the 6th of January. Okay, so I said a few words about the Corona crisis, and you know, it is not well managed in Germany at all, I have to say. Quite contrary to the reputation of this country of being able to organize things like that well. This didn't happen, unfortunately, not on the federal level, not on the state level, not on the city level, and unfortunately also not on the university level. This has, of course, consequences. The first one was that all our preparations for hybrid courses are in vain. But it was also clear to me already before Christmas that even for the final, we can't do it face to face. And how we do it and when we do it, I still have to discuss internally, but we can also discuss it together. So what I announced, that I will offer a Zoom meeting this evening at 5 p.m. And maybe you can tell me your boundary conditions that I should respect. Yeah, so that's about the final. Concerning this lecture, there are 6 lectures to go, and the last lecture would be the February 8th. Yeah, so just after the real end of the Christmas time here. Okay, so with this, let's come to what we did last time, namely, we were looking at the mathematical description of second harmonic generation. So we were looking at the coupled wave equation for second harmonic generation. And here on my iPad, I have them once again. Yeah, so you see, of course, 2 equations, one for the fundamental and the other for the second harmonic. Yeah, so for the fundamental and for the second harmonic. And in order to be able to treat it, we made these equations dimensionless. And therefore, instead of A1, we had U1, which is the dimensionless version of the amplitude. And accordingly also, instead of A2, U2. And then, because U1 was just the magnitude, we also had to introduce the phase. So, and when we did this, then we arrived from these equations to this set of equations. So now 3 equations. And this angle theta, this has to do with phase matching, and phase matching actually will be the central topic of this lecture today. But we assumed that there would be perfect phase matching, and then we come from this set of equations to this simple set of equations. And then we have a very simple solution, namely the secant hyperbolicus on the one hand side and the tangent hyperbolicus on the other hand. And what we see is that we can, at least in principle, deplete the fundamental. When I say in principle, then I mean as long as perfect phase matching is really maintained, and as long as our interaction length is long enough, and so on and so forth. All right. So if we would have an infinitely long interaction length, then it would be possible to convert all the fundamental, so shown here in red, into the second harmonic. Right? So the efficiency of the second harmonic generation can, in principle, be as high as 100%. We made a little example, and we quickly found out that the trees don't grow into the sky, as we say in Germany. Die Bäume wachsen nicht in den Himmel. So you have to take. Yeah, so it's not so easy to, with a simple setup, to get very high conversion rates. This just as a quick reminder of what we did last year. The next chapter then logically would be to look at difference frequency generation, which is also a very interesting process. I don't have enough time to do it, and we rather will do it with a few homework problems, at least a few aspects of difference frequency generation. We said already some words why this is important, so think about parametric amplification, and you'll see in this lecture another example where difference frequency generation is actually very important. So rather than spending 1 or 2 lectures on difference frequency generation, we go, as I already mentioned, immediately to phase matching and look at some details in phase matching. So this will then be chapter 7. And I'll start with a few general remarks. So what phase matching, well, is in a more explicit meaning. So we start with a few general remarks. 7.1, general remarks. Just side remark, I hope that all the technology works. So if somebody could confirm this with a quick remark on the chat, I would appreciate that. Yeah, this sounds good. Thank you very much. Okay, a few general remarks. So we have several waves, 3 waves, 4 waves, and so on. And what we need is to maintain continuity of these waves, right? And this. When we have waves, then the wave, so the argument of the wave is of course omega times t minus k times r, and so from this argument we see already which are the requirements for phase matching. So let us write down this here. So the argument of any wave, we have it in complex notations of any wave function, which means, of course, all the waves in a nonlinear process. In a nonlinear process, is of the form that I just mentioned, namely omega times t minus k times r. And now if we want to have a sustained process where the conditions are all the times the same, then we have to make sure two things, namely that the frequencies match. So in other words, that omega 3 is equal to omega 1 plus omega 2 for a second order process. And we also have to make sure that the wave vectors match, right? So that the vectors k, so that k3 is equal to k1 plus k2. So for a sustained mutual interaction with identical conditions, in wave mixing, over extended periods of time and regions, so space, the frequency matching condition which is omega 1 plus omega 2 is equal to omega 3. And the phase matching condition which is K1 plus K2 is equal to K3 must be fulfilled. And so the first one, so equation 1, the frequency matching condition, this is already been taken care by the coupled wave equation. So we actually use this in order to derive the coupled wave equation. So that's trivial. So what we can now do is that we restrict ourselves to, well, the headline says it already, to phase matching. Most of the time, we'll restrict ourselves to collinear, so to one-dimensional problems. But of course, this is also, phase matching can also be done in 2 dimensions and even in 3 dimensions. And in order to show you what I mean with this, I made a little graph. So this one here. So you see that we have here 2 vectors, k1 and k2. k1 and k2, and if I sum them up, then I end up here with k3. And what I did now, in addition, is to plot the wave fronts for each of these vectors. They are perpendicular on this vector. Actually, I would like to emphasize that I made this here to scale. So the longer the wave vector, the shorter the wavelength, so the shorter the distance between any two of these wave fronts, right? So, and you see that this one here is the shortest, so the smallest, by magnitude, the smallest wave vector, and you see that the distances are the biggest here. Well, and what you now see is that these intersections, well, that they, so that we have here the same phases at all points here in this plane. This is phase matching. So the phases are always the same. So the phases of the different waves, or the relative phases between any two waves, remain the same over the entire interaction region or the entire space. We can do the same thing actually for 3 dimensions, and I'm going to show this a little bit later when we, you'll see why I show the 3-dimensional case a little bit later. So let us write a few notes on that. We will restrict ourselves mostly to collinear waves. However, phase matching can also be realized in 2D and even 3D. Of course, we can add up vectors in 2 dimensions and 3 dimensions. This is actually what they are made for. So now, if we use the collinear case, if we are in the collinear case, then of course, instead of vectors, I can just write the magnitude of the wave number, which is proportional to the frequency multiplied with the refractive index. And this brings us actually right to the problem that we want to deal with today. So for the collinear case, this equation 2 reduces to n1 times omega 1 plus n2 times omega 2 is equal to n3 times omega 3. Right? And of course, if we would have a 4-wave mixing process, then we would just write n omega 1 n1 omega 1 plus n2 omega 2 plus n3 omega 3 is equal to n4 omega 4. So this can be generalized in a straightforward way. So remember, or if we go back quite a bit in the lecture, so we go back to our first solutions of the coupled wave equation. I think this was in chapter 3 or so. Yeah. So yeah, here. Yeah. So what we did here, just as a reminder, we had this sub-chapter here where we looked at phase mismatch in a simple configuration. There we solved the coupled wave equation for under the assumption that the efficiency is low. And yeah, so that A3 is so small that virtually no photons of A1 and A2 are destroyed. And what we found then pretty quickly was that this expression here, and actually I forgot to write down, yeah, so this should have a house number, this equation here, this equation. And you see that we had a few prefactors here. It's proportional to the product of the intensity of the two incident fields. This is not the interesting point here. The interesting point here is how it depends on the phase mismatch delta K. All right, so delta K, this is when this equation 2 of this chapter here is not fulfilled. So when K1 plus K2 minus K3 is not equal to 0, then we denote it as delta K. And what we found is this sinc square behavior. And this is actually of fundamental importance also now. And yeah, it will. So at the end of this chapter, we'll see it once again. So for some frequency generation, yeah, so the thing that I just reviewed in chapter 3, this was for some frequency generation, and it was in collinear configuration. We have done the work pretty much already. We have already calculated the effect of non-perfect phase matching. Yeah, so the sinc term, the sinc square term to be precise, in equation 3.35, and this term, yeah, so all these prefactors I consolidate in this expression here in this variable I3 max. And then we have the sinc squared delta K times interaction length divided by 2. And we also introduced the coherence length, not to mix up with the coherence length known from other fields of optics. Yeah, so this is just by definition delta K, 2 divided by delta K. So the sinc term decides on the efficiency of frequency mixing. Now let's look how severe the problem is. So what delta K in a usual configuration would be. And I just give a quick example. So we just take, well, some material that's not really a prominent nonlinear material, but it's a material that's ubiquitous in optics. So we just take fused silica. Right? And we assume, or we pretend that we would do, say, second harmonic generation in fused silica. This is, of course, nonsense, because fused silica is inversion symmetric and would never produce the second harmonic. But the dispersion of all optical materials, well, is different, but actually not too different, and we just want to get the order of magnitude. Right? So I could have, and perhaps I should, have looked up the dispersion of a nonlinear material, but I just was too lazy to do that. And as I said, it's just about the order of magnitude. So we pretend to stupidly try second harmonic generation in fused silica. And we want to see how severe the phase mismatch problem is. The phase mismatch problem is. Well, we take fused silica. At 400 nanometers and at 800 nanometers. And here at 400 nanometers, I looked up that we would have n equals to 1.470, and at 800 nanometers, it is 1.453, right? And then we can calculate delta K, and we find 2 times 2 pi, and now the refractive index at 800 nanometers divided by 800 nanometers minus 2 pi refractive index of 400 nanometers divided by 400 nanometer. And what we get is 2 pi over 400 nanometers. 1.453 minus 1.470, right? And then what we find is a coherence length of 2 divided by delta K equal to 3.7 micrometers. That's short. So once again, what's the meaning of coherence length? The meaning of coherence length is that if you have a crystal and if you propagate your 3 waves through it, then the sum frequency, the amplitude of the sum frequency would grow for a propagation distance that's equal to the coherence length, and then it would get worse again. Then energy would flow from the sum frequency, so from omega 3 back to omega 1 and omega 2. Right? So this means that the efficiency is actually limited to interaction lengths not longer than a few micrometers. If you take some other material for which second harmonic generation would make sense, yeah? If you take a nonlinear crystal and you look up the dispersion curves, then you see similar numbers, certainly not the same. Well, then it's perhaps just 2 micrometers, or if you are lucky, then it's 5 micrometers. But it's something in the order of just a few micrometers. Yeah? This doesn't look very good, right? And, well, there's a famous figure in literature, which I'll show now. So in the very early days of nonlinear optics, people tried, of course, how the second harmonic, for example, behaves. And here is a respective graph from a paper in 1961, right? And the idea was, of course, to make this, or to test what we just discussed by increasing the thickness of the crystal. This is, of course, difficult. It's much easier to just put the crystal into the beam and to tilt it such that the beam propagation gets longer. And this is what people did. And what they got is this figure here with these fringes. It was a PhD student who did this, and his name was Paul D. Maker, and therefore these are called the Maker fringes. Yeah, so Maker fringes. So, and I looked up the guy and finally found him on Wikipedia. No, not on Wikipedia. I found him on Facebook, actually. So once again, this here is Paul D. Maker. I didn't find any dates here, right? So I just guess from the few details he provides on Facebook. Maybe I contact him via Facebook one day. I guess that, so that he's close to 90 years old now. And, well, here this paper published in Physical Review Letters on the 1st of January of 1962. So this was an important part of his PhD thesis, I think. What's interesting here is his affiliation. So he did his PhD at the University of Michigan in Ann Arbor, so close to Detroit. So he was, or at least his supervisors, they were with the Ford Motor Company, and they had a scientific laboratory at that time. Well, they certainly still have one today, but I guess none in the fundamentals of laser physics, like at that time. So one of the older guys there, perhaps a postdoc at that time, certainly a postdoc, Terhune, I don't know how one would pronounce his name. So he was actually also the founding editor of optics letters. Yeah. So and there's you can find a very interesting interview about his career in war times and in a difficult family situation. Quite interesting to dig out a few of these people. Well, and now, why were they interested? Why was Ford interested, the Ford company interested in nonlinear optics at that time? Well, these two people, they discovered something else, and this brings me back to phase matching in 3D. So here, once again, phase matching in 2D and in 3D. You can, of course, organize or arrange the different waves, here 4-wave mixing, in this way, so that two of these waves are in one plane that's perpendicular on the other plane. And the process that you can investigate with this is anti-Stokes. So what you can do is anti-Stokes spectroscopy. Yeah, so like depicted here. So you would shine in here several fields. So in this case, 3 fields, and then you get out the 4th wave here, which carries the spectroscopic information. And so, for example, you would use here these 2 pump waves, right? And then tune this wave, and then wait until you get this wave. Yeah, tune this wave such that you get this wave. And of course, you need to phase match this But this gives a nice opportunity for background suppression, right? And they do it in this way, as depicted here. So they come in with these 3 fields here, and then you know exactly in which direction the other field has to come, and therefore you can put a mask that blocks all the other radiation, right? And this is called coherent anti-Stokes spectroscopy, and if you do it in this special form, then it's called boxcars, yeah? A famous spectroscopy method in physical chemistry, for example. And so this gives you an idea why cars, probably not boxcars at that time, why cars was also discovered by these 2 people here, by Maker and Terhune and others, because they were, of course, interested in time-resolved analysis of the combustion processes in a motor. So for a far-sighted management at that time, this was actually a very far-sighted management at that time. So just a few days, more or less, a few months after the discovery or after the invention of lasers, to think about these processes. Okay, so you see, the normal situation would be that we have a huge phase mismatch, and therefore the prospects of nonlinear optics are per se not so great, right? And we have now to think about ways on how to overcome this, on how to construct a situation such that the phase mismatch can be made 0. And there are several methods to do that. Basically 3 methods there are, and one is critical phase matching. The other one is, of course, non-critical phase matching. And then there's also quasi-phase matching. Okay, and we start with critical phase matching. It's also called angle tuning, and we'll develop this at the example of second harmonic generation. So 7.2, chapter 7.2, phase matching for second harmonic generation by angle tuning. So the first thing, and this actually goes back to the little example that we calculated, this half-stupid example that we calculated for fused silicon. So if we speak about optics, then most of the time we are in the regime of normal dispersion. Normal dispersion means that the refractive index increases as we increase the frequency. Right? And this is actually the problem. So you see this actually here, right? So for 800 nanometers, the refractive index was a little bit smaller than for 400 nanometers, but this little difference is more than enough to almost discourage nonlinear optics. Yeah? So this is a very general behavior that the refractive index, at least in the visible region, increases with increasing frequency or decreasing wavelengths. So this is the underlying problem. So optical engineering usually takes place a little bit takes place in the regime of normal dispersion. Yeah, which means n, the refractive index, increases with frequency, so with the frequency omega. Yeah, and therefore, well, this seems to prohibit phase matching for second harmonic generation. Yeah, because, of course, the refractive index for 2 omega is larger than the refractive index for the fundamental. Well, fortunately, there is birefringence. So in birefringence, for one material, you have 2 refractive indices for, of course, different polarizations. Yeah? So this is one way to overcome the problem. Well, actually, birefringence is pretty much at all the approaches that are possible, so that are so thank you, Frau Hopfe. So my tea is already here. So a break is in 5 minutes or so. We'll have a break. So birefringence is actually at the root of all, or pretty much all, options to achieve phase matching. May it be critical phase matching or non-critical phase matching. So birefringence offers 2 indices of refraction and thus can solve the problem. How? We'll see. So first, a quick graph here. So we have the situation. We have this situation here. Yeah, so you remember chapter 1, I reviewed birefringence, and now you see why I did this. Of course, I mentioned it at that time already. So if we have a birefringent crystal, then we have, as I said, 2 refractive indices for each wavelength, and of course they behave in the same way. So this means that the refractive index for the ordinary polarization goes up with frequency, as does the one for extraordinary. And yeah, so the ordinary wave and the extraordinary wave, yeah, so the refractive index, if the refractive index for the extraordinary refractive index is higher than the one for the ordinary refractive index, then we call this positive birefringence. And in the other case, we call it negative birefringence. It's just the name, right? And now, you see, if we would come here for this crystal, for this positively birefringent crystal, if we come here with the fundamental and take the polarization of the fundamental such that the extraordinary index of refraction applies, then if the second harmonic is has its polarization in the ordinary direction, and well, if we are lucky, actually if we are very lucky, then you see that we have here the same refractive index. Well, for a negative crystal we can of course do the same thing. Well, then we have just here the ordinary and here the extraordinary beam. Of course, you see that this would be great luck, right? So we would, in order to do this continuously, we would need an infinite amount of crystals, which we do not have, of course. So we need to do another thing, but actually birefringence immediately offers a solution to that, because by changing the orientation of the crystal, we can go from the extraordinary refractive index continuously to the ordinary refractive index, and well, if both curves cross, then we achieve phase matching. So with this, I would do 5 minutes of a break, so you can cook your coffee or tea and come back in 5 minutes with a cup of coffee or tea, some cookies, whatever you like. So see you in 5 minutes. So let's continue. So what we can now do with, in order to achieve phase matching, would be to tilt the crystal, to tune the angle. So therefore one also speaks of angle tuning for phase matching. So to tune the angle such that the ordinary index of refraction, or the effective index of refraction of the extraordinary wave, I wanted to say, equals the one of the ordinary index of refraction. So that would be angle tuning. So n of 2 omega equals n of omega can be achieved by tilting the crystal, and this is called angle tuning. Because the extraordinary index of refraction is a function of the relative orientation of a beam and the crystal. So just to show this on a graph, the following figure here. So we have a crystal here, and its optical axis is this horizontal line here, and I also plot here the indicatrix, right? So this ellipse. If we look in direction of the optical axis, so for the front view, then the cross section of the indicatrix with a plane that is perpendicular on this vector k is a circle, right? So in this direction, we have the ordinary index. Yeah, so in this, for this cross section, the refractive index is independent of the polarization. So whether you choose the polarization like this or that, or you always have the same index of refraction. However, for the other polarization, so for the polarization like shown here, yeah, so here we have the D vector, there the index of refraction changes, and it changes here from the ordinary, from the value of the ordinary one to the extraordinary one. So I can tune the refractive index from this value here to this value here by tilting the crystal. Right? And what you now can do would be to plot the index of refraction as a function of this angle. Right? So we vary this angle here from 0 to 360 degrees. Right? We rotate this vector, this wave, or we rotate the crystal by 360 degrees. Then for the polarization that's perpendicular here on the optical axis, the refractive index, which is the ordinary one, does not change, right? So this means that if we do this and plot the refractive index, because it doesn't change, we get a circle. Well, if we do this for the other direction, then we get, of course, this ellipse here, right? If we have positive birefringence, right, then the extraordinary refractive index is larger, and this you see immediately, right? So if we try to draw this circle here into here, then we get this figure here, right? In the positive case, yeah, so this is the same thing here. Yes, so this is right. So for negative birefringence, the extraordinary index of refraction is smaller than the ordinary one, and here this circle would look like this. Right? Okay, and with this we are almost done. So let us write a few words on what we discussed just. Using the indicatrix, we can construct the dependence of the ordinary and extraordinary index as a function of the direction of k or equivalently this angle theta, yeah, so this one here, so here. Yeah, and in case of the ordinary beam, yeah, so the k vector with the polarization, in this case here pointing perpendicular to the plane of drawing. So in the case of the ordinary beam, this will be a circle. With radius equal to the ordinary index of refraction, right? And for the extraordinary beam, we get an ellipse. For the extraordinary beam, we get an ellipse with half axis equal to the ordinary index of refraction and the extraordinary index of refraction. And with this, we are more or less already done. Because we can make the same figure for the fundamental and for the second harmonic. And this looks like the following. Oh, I forgot to copy this. This is unfortunate. This is very unfortunate. If this is so, then I have to try to draw this by hand. Perhaps this thing here helps me a little bit. So then we would have this situation, and now I'm afraid that so we have this situation. And now if we draw it for the second harmonic, we know that the refractive index is larger. So I would draw a circle like that. Yeah. And well, the important thing is already visible. The important thing are these crossing points here, right? So for these directions, the refractive index of the second harmonic and of the fundamental are equal, right? So I don't even need to draw the blue ellipse in this case. So yeah. Yeah, so for these points here, we would have phase matching. And what we have here is positive birefringence. So 5, and so 4 positive birefringence. The ellipse of the fundamental can intersect the circle for the second harmonic. And vice versa. So for negative birefringence, you would intersect the circle of the second harmonic with the ellipse of the fundamental. And it's quite easy to calculate actually these 2 points, because what you need to do is just to intersect an ellipse with a circle, and we know, of course, the equation for both. So the directions or the angles theta for which in this case it's an O of 2 omega equals an extraordinary of omega, yeah, can easily be derived. Yeah. So, for example, for negative birefringence, so for the other case, there we would have that cosine squared of theta divided by NO squared plus sine squared of theta times NO squared. So this is a circle here, must be equal to, and now the blue circle, and I also write the formulas in blue, cosine squared of theta divided by NO squared plus sine squared of theta divided by NE squared. Or the one in Z direction. And from this, one quickly gets that the sine squared of theta is equal to 1 over NO squared minus 1 over, I have to do this in colors, otherwise they look the same. Minus 1 over NO squared at the second harmonic divided by 1 over NE squared minus 1 over NO squared for the blue direction. Yeah. So this is pretty straightforward to calculate, but of course one should have seen this once and should be aware how this works. Let us do a little example. We use a common nonlinear crystal by the name KDP, and try it out. Example KDP, and we assume the following, namely a wavelength for the fundamental of 693 nanometers, and then of course a wavelength of the second harmonic of 347 nanometers. You can look up the refractive indices. How do you get them? We'll come to that later. Sellmeier equations, and you need the Sellmeier coefficients. So the refractive index of 693 nanometers, this is 1.506, and at the second harmonic it is 1.534, and we can also do this for the extraordinary refractive index. There it's 1.466, and here it is 1.490. So you see that the extraordinary refractive index is smaller, so we have positive birefringence, negative birefringence, of course. So then we can calculate theta, and what we find after some, so just plugging in the numbers, would be then 53.7 degrees Celsius. And well, one has to tune this angle pretty exactly, otherwise there will be no phase matching. Okay, so what we assumed without saying much about it was that the fundamental wave, that the fundamental wave has a polarization that's in, I should start differently. So say we would start with some frequency generation. Then you also could assume that we play a little bit more with the polarization. Then we could say that we use, for the polarization of the two small photons, of the two incident photons, we might use a different polarization, right? Or we might use the same polarization. And in order to discuss all these different possibilities on how to choose the polarization, one introduces a special nomenclature. One speaks of type 1, type 2, type 3, and so on, phase matching. The most frequent ones are actually just type 1 and type 2. So this would be the next point here to write up, namely the nomenclature for phase matching of three-wave processes. For phase matching of three-wave nonlinear processes. So the first thing to say would be that we mostly use uniaxial crystals. Also, there are quite a few biaxial crystals that are also interesting for nonlinear optics. Yeah? So when I say that in practice mostly uniaxial crystals are used, then this applies well, approximately for cases where one does angle tuning. When for non-critical phase matching, actually biaxial crystals are more frequent. So in practice, at least for angle tuning, mostly uniaxial crystals are used. And this means that each of the three waves can be an ordinary or an extraordinary wave. Ordinary or extraordinary. And therefore, we label the process just in this way. So instead of writing omega 1 plus omega 2 equals omega 3, where the polarization is not clear, we write E dash O goes to O, right? Which means that omega 1 is extraordinary, omega 2 is ordinary, and omega 3 is also ordinary. Yeah. So the different possible processes are labeled accordingly. Yeah. For example, we would have E, O goes to O, which means omega 1 is extraordinary, omega 2 is ordinary here, and omega 3 is also an ordinary wave. Yeah? And the convention is that the first And so you can always rearrange an equation. But the convention is that we take the small photons on the left side of the equation and the big photon on the right side of the equation for a three-wave process. Yeah, so the first two letters, so the, perhaps, yeah. So for short, sometimes this is written as EOO, and here, but also above, the first two letters refer to the small photons, loosely speaking, to the photons with the long wavelengths. And now for difference frequency generation, actually the same applies. For difference frequency generation, we start with a big photon, and it is split into two small photons, right? So this convention also applies to difference frequency generation. To difference frequency generation, where a big photon is destroyed and two small ones are created. So explicitly, one could write so EO and then the arrow in the other direction. However, one mostly sees in the literature EOO or just EOO, right? So, and now, if the two small photons have the same polarization, then we speak of type 1 phase matching. And if this is not the case, if they have different polarization, then we speak of type 2 phase matching. Right? And this is frequently seen in practice, in the literature, of course, but also in the lab. Right? And I will show one example where this is particularly, where the consequences are particularly striking, whether you use type 1 phase matching or type 2 phase matching. So type 1 phase matching the polarization of the two small photons is the same, and type 2, well, where their polarization is different. And if we discuss this for the special case of second harmonic generation, then we have the following scenario. Of second harmonic generation. Yeah. So we have this here. So, type 1, there, the fundamental, they have the same polarization, right? And of course, the second harmonic has to have different polarization. And what you see is that this case, OOE, is only possible for negative birefringence. So this is actually what we saw here at this graph, right? If we have here, so here this is actually positive birefringence, right? So extraordinary index is larger than the ordinary index. Therefore, the fundamental here is the extraordinary wave, right? Yeah, so the fundamental is the extraordinary wave, and the second harmonic is the ordinary wave. So this is exactly reflected here, right? So here, for the positive case, it's the extraordinary wave, and for the second harmonic, the ordinary wave. Well, and if you look at the crystal, so this is supposed to be the crystal, the beam goes through like this, right? And we have, if the polarization would be this one here, then what we would get out for the second harmonic would have a polarization that's perpendicular one on the polarization of the incident wave, right? And if you look at the phase, at the exit phase of this crystal, then you would see this situation, right? So this polarization would be this one here, and this one here, actually, of course, this one here. Right? Conversely, for type 2, phase matching, for second harmonic generation, you might ask, how should it be possible to say that one photon, one of the small photons, is in ordinary and the other in extraordinary polarization? Well, you see what you have to do. You have to use the polarization at an angle, say at 45 degrees, and this would then correspond to type 2 phase matching. An example for that, actually a pretty striking example for that. So this is what you see here in a second. Yeah. So what you see here is down conversion. So a special form of difference frequency generation. What you do here is that you pump a crystal with a short wavelength, for example, right? And then it decays into 2 photons. For difference frequency generation, you usually would use here also the signal wave here, and then generate here. Yeah, so you would come in with 2 frequencies in order to get out the difference frequency. Here, this field is played by the vacuum, actually, right? And now the interesting point is, if you do this in type 1 configuration or in type 2 configuration. In type 1 configuration, you get out one cone, and in type 2 configuration, you get out actually two cones, where one has vertical polarization and the other has horizontal polarization. What's interesting about that? Well, interesting about that is the intersection of both cones, because there you have kind of both polarizations. So there's a if you have a photon there and you measure it with, say, vertical polarization, then you know that the photon here would have horizontal polarization. Yeah, so the photon pairs that are created here and here, they are entangled, and here the entanglement is coded in the polarization. And this is a very convenient way to produce entangled photon pairs and to use them. So in quantum information, this is a very a very famous scheme here, but also in quantum communication, quantum computing. So this scheme is here frequently used. Also, ghost imaging is a new application of a photon source like this. Yeah, single photon sources can also be produced in this scheme. Yeah? And so it's a striking difference here between type 1 and type 2 phase matching. Good. With this, we would come to the next paragraph, namely non-critical or 90-degree or temperature phase matching. So, and the idea is the following. I can show this very easily here at this graph. So what we have here is are the dispersion curves of a special crystal, namely potassium niobate. And this is a biaxial crystal, and you see that that we have here the dispersion for the direction in the the orange one here is actually the A-axis, right? So the crystallographic A direction. Then the green one is the B direction, and C, this is here the violet dispersion curve, right? And what you see here, and what is indicated here, is that you can change this here by heating the crystal. Well, an intuitive way to understand this would be that if you heat a crystal, then it expands, right? And therefore the crystal lattice changes, and therefore the refractive index changes, right? And you see that the effect is the biggest for the C-axis, and I'm pretty sure that this crystal expands in the C-axis more than in the other two directions if you heat it. Yeah? And what you also see is that I've drawn this here for the range of 1,000 to 700 nanometers, and for 500, well, which is just half of that, the second harmonic of 1,000 nanometers, to 350 nanometers, which is the second harmonic of 700 nanometers. And what you now can do is that you overlap them, yeah, like shown here, and then you see where you have so where you can phase match the second harmonic. This line here, yeah, so let's go back, right? So you see that the steeper lines, they correspond to the short wavelengths region, to the second harmonic. And now you see that, for example, here you have overlap, so here you have identical refractive index. So this would be non-critical or 90-degree phase matching, or temperature phase matching. One has to control the temperature quite precisely, to a fraction of a degree or so, right? And non-critical phase matching has particular technical advantages, and therefore it's, and we'll see what these advantages are. The walk-off problem. So if you use birefringence and you don't go in the direction of the semi-axis of the index ellipsoid, then you see, well, birefringence, namely that the two beams for the different polarizations split, and this can lead to the situation that the beams for the second harmonic and for the fundamental, that they don't overlap any longer spatially. And then, of course, the interaction kind of is gone, right? So this is a limitation for the efficiency. This can't happen for non-critical phase matching. And therefore, if you build a laser that's diode pumped, but you need the second harmonic of that, right? Then you would frequency double the fundamental, the diode laser radiation. But you would try to do this with non-critical phase matching, because there the efficiency, this has advantages in terms of efficiency. But you need then to heat the nonlinear crystal, and and this has its own difficulties, because usually these nonlinear crystals, they are coated with an anti-reflection coating, and the anti-reflection coating has a different thermal expansion coefficient than the crystal usually, right? And therefore, if you heat it, in particular if you heat it several times and cool it down several times, then this coating will detach from the crystal such that the thing is destroyed. So therefore, one needs quite some technical efforts in order to realize this. So one has to heat the crystal, and one should never switch it off. Even if the power goes down, there should be emergency power for such a device, such that it is not heated up every day when you switch on your laser. So these are the difficulties with non-critical phase matching. And maybe just for to conclude this this lecture, I would like to introduce to you a famous Chinese scientist who invented several nonlinear crystals. One is LBO, which is also frequently used in newer times for non-critical phase matching. There's also BBO, which is one of the most widely used nonlinear crystals. And finally, there's KBBF, which is very important for UV, for frequency doubling in the UV, which of course has a huge importance for lithography, but apparently also important military applications. And so the Chinese wouldn't export these crystals to the US. So for the first time, it was the case at the turn of the century that China would say no to export requests from the US. and not vice versa. So a famous person in nonlinear optics. Also for the theory of these crystals, so which is very advanced physics. With this, I conclude this lecture. I will send around a Zoom link for answers and questions session at 5. It's of course completely up to you whether you want to participate or not. Thank you for your attention.